Introduction to Optimization, Questions for Screen Recording Task. Part 1, Gradients and Hessians. The first question, develop the formula for the first and second directional derivatives. Let f be a function of the variables x1 to xn. We will give it the notation of f of x1 to xn. The differential of f will be the derivative of f by x1 multiplied by the differential of x1 plus the derivative of f by x2 multiplied by the differential of x2 until we get the derivative of f by xn multiplied by the differential of xn. This sum can be written as an inner product of two vectors, where the first vector will be the derivative of f by each element, and the second vector will be the differential by each element. So the left vector of the inner product can also be written as the gradient of f, and the right element can be the differential of the vector x. So by the definition of the inner product, we can also write it as the gradient transpose x multiplied by the differential of x. The gradient will be annotated as g. The external definition of a gradient. Let alpha be a scalar and let r be a direction vector. We will define phi alpha to be f in the point x0 plus a step of size alpha in the direction r. We will derive phi by alpha, and we get the first directional derivative of f in point x0. That equals to the derivative by alpha of f in point x0 plus alpha r. We will annotate x to be x0 plus alpha r and get the differential of x will be r multiplied by d alpha. So the differential of alpha will be the differential of f in point x0 plus alpha r. And we calculated in the previous slide that the differential of f is g transpose x0 multiplied by the differential of x. So it equals to g transpose x0 multiplied by r d alpha. And that is because the differential x equals to r multiplied by the differential of alpha. And that expression can be written as the inner product of gx0 r transpose multiplied by the differential of alpha. And so we got that the first derivative of phi by alpha is the derivative of phi by alpha, and it equals to g transpose x0 multiplied by r. So for conclusion, we got that the first directional derivative of function f in the direction r from point x0 is g transpose in point xfs multiplied by r, point x0. Okay. So the differential of the gradient. We saw that the differential of f is g transpose dx, and we will prove that the differential of the gradient g is hx multiplied by dx. We will define the Hessian to be a matrix where each element is a second derivation of the original function f. So the first element is a second derivation by dx1 and by x1. And the second element is the second derivation of f by x1 and x2 until the last element of the first row will be the second derivation of f by x1 and xn. And we continue for the second row and the last row until we get the last element in the matrix, which is the second derivation of f by xn and xn. Now, each element of the matrix can be written as a derivative of an element from the gradient g. So the first element is the derivative of the first element of g by x1, the second element in the first row, will be the derivative of the first element of g by x2, and the last element of the first row will be the derivative of g1 by xn, and we continue until the last element of the matrix, and this will be the derivative of the last element of g by the last element of x. Now, each row can be represented as a gradient of the first element, as a gradient of an element from G. So the first row is a gradient of the first element of G, the second row is the gradient of the second element of G, and the last row will be a gradient of the last element of G. So because our default vector is column, and here we can see we have rows, we will annotate the first row as the gradient of G1 transpose, the second the gradient G2 transpose, so on until the gradient of Gn transpose. And this is the definition for the Hessian Hx. So the differential of the gradient will be h multiplied by dx, which is the vector of the gradients of the gradient elements of G, multiplied by the differential of x. Now, this is a multiplication that can be done element-wise. So the first element multiplied by dx, the second element multiplied by dx, until the last element is multiplied by dx, and we get this vector. For example, the first element of this vector is gradient of G1 transpose dx, and so on until the last element. And we can see that each element of the vector is actually a differential of an element from the gradient G. So it's dg1, and the second element is dg2, and the last element is dgn. So we get that this vector, h dx, equals to the differential of the gradient G. Now we will derive the first directional derivative of f. So we have phi tag alpha, and we are going to derive it again for the second derivation. So we are going to have a directional derivative of the first directional derivative of f in point x0. That equals to the second derivative by alpha of f in point x0 plus alpha r. And that equals to derivative by alpha of the first directional derivative of f in point x0 plus alpha r. So we know that the first directional derivative of f is g transpose x multiplied by r. So since this is an inner product that gives us a scalar, we can transpose it and get the same scalar. So we are going to write the first directional derivative of f in point x by g transpose x r, and we are going to transpose this expression and get r transpose gx. And then we can conclude that the differential of the first directional derivative of f is going to be r transpose multiplied by the differential of g. And that is since only g depends on x, r is independent of x. So the differential of the first directional derivative of f, as we saw, is going to be r transpose multiplied by the differential of gradient g. But we calculated earlier that dg equals to hx0 dx. And then we know that dx is actually equals r d alpha. So we can see this expression here is going to take dx and transform it to r d alpha. Then we can see that this expression that also written here can be written as an inner product of two scalars. The first scalar is r transpose h x0r, and the second scalar is the differential of alpha. this expression here is a scalar. And also, we know that H is a symmetric matrix, so H transpose X equals H. And then we get the differential of the first directional derivative of F equals to an inner product of R transpose H X0 R and the differential of alpha. So, to conclude, we got that the second directional derivative of F is R transpose H X0 R, where R is the directional vector and H is the Hessian matrix as we defined.